present in setting cement pastes, which are precursors for ceramics, so clay-like materials. So before you bake the tiles on the space shuttle, they are made of a fluid or paste, which is very like this. All kinds of things, wellbore fluids, and increasingly in energy materials as well. So when you're processing any of these kind of soft composite materials, it often is a target to get as much solid content in there as you possibly can, whilst remaining processable. And so what this theoretical insight is telling you is that if you want to do that, you have to think about the detailed physics of the contacts and try to turn down the friction by whatever means is available. Okay, so I've come to the end of my story. This is the same as my initial slide, and thank you for your attention.
Open the floor to questions, both online and right here at the microphone. And Abe, you're on. Just one, maybe two.
You mentioned how the liquid crystals are shaped like needles. How do they behave? Because the needle shape would it cause more block-ups because they would block each other much more often?
So that's a very good question. So there are two different kinds of liquid crystal. The ones that you have in your phone and laptop display, these are actually, they're rod-like molecules. And because they're so small, actually there's basically no friction between those molecules. So the liquid crystals which are used in displays are, they tend to make these swarms of aligned rod-like molecules, and then with an electric field, actually this is all on the blackboard behind me, with an electric field you can turn them one way or turn them the other way, and that's what happens in a liquid crystal display. But you can make and find in nature systems which are like this, where you have quite big particles which are rod-like, and then you can see the jamming effect at a much lower concentration. So it's like the log jam on the river that I showed you. You can get a tangled network of jammed sticks at a much lower concentration than you need to go to get a locked packing of spheres.
Thank you.
Thank you.
Very good. Thank you, Aidan. I have a question about what drew you to fluid dynamics.
Yeah, this is interesting. Well, so I was aware of this behavior from about the age of 10. And I don't think I saw it at a science fair or at a school's lecture. I think I saw it in my kitchen. So it was kind of the back of my mind for a long time. But I would be a sad person if I admitted that I'd spent 45 years trying to understand precisely this phenomenon. But it's possible that that was among things that drove me in that direction about sort of PhD time. So at that time there was a guy called Sam Edwards in Cambridge who died last year, unfortunately. But he had this confidence that, you know, real theoretical physics, again, of the kind you see on the blackboard, which apparently is also by me, could be used in his case it was this problem of entanglement in polymers. And so that's what I did my PhD on, and that got me hooked.
Let's take a question in the house.
Yeah, hello. Your lecture reminded me of something, a technique I used 40 years ago in die sinking. And the way that worked was to sink a positive model into a block of steel under an enormous amount of pressure.
Right.
And lo and behold, after about 3 months, in this press, a die sinking press or coining press, it yielded actually to the positive and pressed into that block of steel. I think it was somewhere between half and an inch deep. That would rather be the reverse of what you lectured on tonight. What is involved here?
So you're talking about then something which is baseline solid that can liquefy if I abuse it or was subjected to extremely high conditions. So, okay, so that's something that we also have a bit of experience working on, but mainly in the case where the solid is amorphous. So if you ask me that question about a glass as the solid, I could give you a fuller answer. But for the point of view of the mechanics of steels and the like, there, because you have a crystal lattice, the ability of that to slowly adapt its shape when you're, say, forcing this other object into it is to do with the plastic flow, which involves understanding the nature of the dislocations in the crystal lattice and how those gradually migrate to allow it to flow from one shape to another. So it's obviously a related problem. As you say, it's the kind of inverse problem. But because the starting solid material is crystalline, the actual mechanism for how that flow is able to arise is somewhat different from the kinds of thing that happens in these suspension systems where the basic structure is always disordered.
We have a question from the online audience. Have the ideas that you've explained here tonight been put to use to prevent disasters like landslides?
Well, that would be rapid progress. Since the work that I described was published only in 2014. So the answer is no. And it's an interesting question, though, is you know, how much more would we need to understand to be able to get to grips with that? Now, again, landslides, again, is one of these reverse problems. It's where you have something which is a solid, and it may be a rather tenuous solid. So wet soil is a solid in a rather miraculous way. It's because you've got quite a lot of fluid there. You may have air as well. You have particles, which in this case tend to be adhesive. So the landslip I showed you, which again is the complement of this problem, is one where you have contacts between particles which are sticky, and then under some state of stress or flow, somehow there's a feedback which brings all these contacts up. So that's a problem we're also interested in, but it's a sister problem to the one that I talked about.
Yes. Thank you for a great lecture. I'm wondering about nano possibilities, or say surfactants, nanotechnology to change the flow patterns of these. Is that something we're looking into?
Well, so there's two avenues there. One is to think about the flow behavior of systems where the particles are really small. And as you get down towards a molecular scale, what happens is that you have more and more Brownian motion on the scale of your particles, so that they are thermally whizzing around. And that means that actually this idea of a sort of fixed mechanical contact becomes washed out, if you like, in this Brownian motion. So if you shrink the particles in this system down to this, the scale for Brownian motion being important is a couple of hundred nanometers. If you go down to 10 nanometers, it's dominant. And then you can also get this type of behavior, but the mechanism is somewhat different. And it's to do with overcoming the fact that you have a jammed phase, which is not a mechanical jam. It's more like a glass. It's got particles that, in principle, can move, but each is in a cage created by its neighbors. So then the solid phase is an amorphous but highly dynamic solid, in which the important thing is that the particles can't swap places. And then if you come with a stress, you can melt that. But there are also systems, we think, where you can make it go through the glass transition in the other direction. In other words, it will be the Brownian motion will be impeded because of the stress you put on, essentially because you're making it anisotropic. So there is a sort of sliding scale from this right the way down to the nano regime. And of course, if you're starting to talk about the physics of contacts and engineering the contact friction, that's basically nanotribology as the field. So at that scale, the molecular details matter.
That's why I was kind of wondering about nanoparticles that are acting as like a surfactant onto the larger particles to adjust the slipperiness of flow.
Yes, so you could imagine them being like ball bearings, perhaps, and that's an interesting idea. There's been some speculation that micelles could play that role. In fact, you might think that micelles of lecithin could play that role, and we have no proof that that's not actually what the lecithin does in the chocolate system. We don't know. Yeah, so it could be that thing.
Thank you. Let's take one more question from inside.
I would like to ask probably the least technical question ever asked at Perimeter Institute lecture. we have come to these lectures for years and years, and usually they're of the nature of, don't try this at home. I'm really curious to know, and I know this is not a cooking show, but what would the recipe be for mixing starch and water to get that effect that you had there?
That's a great question, and actually the answer is really easy. So what you do is you start with the starch. It's like the initial steps of making a white sauce. You start with starch. You add water more or less drop by drop. Just a little, and you get to this. And if you've added a little bit too much, you'll find that you can pour it a bit too easily, and it doesn't have quite such a nice. I'm going to just do this again. See, a little bit came to the top there. So if you see something which doesn't do that, then you've added a bit too much water, so put a bit more cornstarch in. And that's really all there is to it. And I was doing this before, obviously, preparing this, and it did, on this scale, like 3 liters, it did take me 45 minutes to get it right. But in your kitchen with a smaller amount, you can do it in 5 minutes.
Fantastic. Thank you. Very good. Ladies and gentlemen, Dr. Michael Case. Thank you very much. To the Mike Lazaridis Theatre of Ideas here at Perimeter Institute for Theoretical Physics in Waterloo, Ontario, Canada. And welcome to this Perimeter's public lecture series presented by BMO Financial Group. My name is Greg Dick. I'm the Director of Educational Outreach here at Perimeter, and it is a pleasure to welcome everyone here this evening. Both those of you here in the live studio audience and those of you watching online, whether on Perimeter's website or on one of our many science communication colleagues' websites around the globe. The lecture itself will last approximately 1 hour, and there will be time for question and answer at the end. For those of you watching online, Dr. Damien Pope and a team of PI researchers are behind their keyboards. They're monitoring the Facebook and the Twitter feeds, and will answer questions and engage in discussion throughout the lecture and even a little bit after the lecture as well. So if you want to join that conversation, please use #PILive. And now it is my pleasure to introduce tonight's very special guest speaker, Dr. Michele Mosca. Dr. Mosca obtained his doctorate in mathematics in 1999 from Oxford University on the topic of quantum computer algorithms. His research interests include quantum computation and cryptographic tools that will be safe against quantum technology. He is globally recognized for his drive to help academia, industry, and government prepare our cyber systems to be safe in an era of quantum computers. Tonight, Dr. Mosca will explore quantum technology, both those that already exist and those that are yet, and how they will affect our lives. Ladies and gentlemen, please welcome Dr. Michele Mosca.
Well, thanks so much for that very warm welcome and for spending your precious time here with us today. I want to talk about the implications of this new paradigm for physics that was discovered roughly a century ago. A new paradigm is slightly different from a new theory. A new paradigm is a mathematical framework in which to express theories, discover and articulate theories. It's like a new language. Okay, so a simple example of a paradigm that we use is, say, or have used in the past, is the flat Earth model, the flat Earth paradigm for describing the surface of the Earth. It tends to serve us well if we're describing small regions of the Earth. So we take accurate pictures of actual reality and we try to draw it on a flat Earth, a sheet of paper, and it works more or less, except when you push it to the limits, then something goes wrong. And what went wrong wasn't the person taking the measurements made a mistake. There's no numerical calculations. It was just you shouldn't be embedding it on the flat surface. You need to embed it on a sphere. The sphere is a new mathematical paradigm, which is a more accurate paradigm for expressing the surface of the Earth. A new paradigm are generally accepted, are not accepted because their opponents see the light, or rather their opponents die off. And the new generation are often familiar with this. Quantum mechanics, so why not just be part of the new generation? Mine once told me, people don't change their behavior because they see the light. They change their behavior because they feel the heat. So, I started to feel the heat of quantum mechanics later on when I realized what its implications were for computation, communication, and cryptography, which I did care about. I'd invested 3-4 whole years of my life in this field. It seemed like a long time for me. So I was like, well, there's got to be something wrong with this, right? So why does quantum theory affect computation? Well, computation is a physical thing. You store information in a physical medium, you manipulate it according to physical processes, you get some sort of answer, and so on. So you can't have a theory of computation and communication and information divorced from a practical theory of physics, a practical framework for physics. And when you look at the implications of quantum theory on computation, you actually get a fundamentally new mode of computation. There are serious implications, which I'm going to talk about today. I didn't like those implications because it changed what I was doing very fundamentally. But I did after a few months of my supervisor insisting I read up on things before I dismissed them. I did eventually see the light, and I started working in quantum computing. This is, by the way, a photograph that my colleague Matteo Mariantoni and collaborators took of a 4-qubit superconducting, computer chip. There's four little loops here. Those are quantum bits. The wiggly wires allow them to interact, and so on. You can do more quantum bit computations. So we've gone, as you can see here, 100 years ago we learned that there was a new game for physics. We learned the rules of the game. But it took over a century to start really playing the game and controlling things in a very quantum mechanical way. So we're entering what some people call the second quantum revolution, where we can actually store and manipulate things and have very complicated, sophisticated quantum effects that don't naturally occur in nature. And this new paradigm for computation, I initially did not like it, but I eventually realized it actually brings a wonderful host of new possibilities for science, technology, and humanity, which I'm going to talk about for the next little while. So what is it that's underlying quantum mechanics? Why did we need a new paradigm? What was wrong with the old language? It didn't allow us to express a very simple feature of physics, namely that a physical system that can exist in two or more distinguishable states can in a special way embody distinguishable states at the same time. I'll try to give you a sense of what that means, but obviously it's not so simple, and of course we invented a new paradigm because we couldn't express it in terms of the old paradigm. So imagine a bit of information, a 0 or a 1. It's encoded in some physical medium. For example, an electron in the ground state, or in the excited state of an atom. It's a perfectly good bit, physical embodiment of a bit. Quantum theory says that such a system can actually be in a state like 0.7071 ground state minus 0.7071 excited state. What does that mean, right? And why those weird numbers? Well, those are square root of a half, square root of 0.5. So we'll see in a minute why I picked those numbers that way. Well, and what does minus mean? We know what probabilities are, but these aren't probabilities. These don't add up to 1, right? Add up to 0, actually. So what does that mean? Probabilities should add up to 1. You add up the probability of the Chicago Cubs winning the World Series and the probability of the Toronto Blue Jays and then the Texas Rangers. I hope their probability is 0, but it isn't. But it adds up to 1. If you look at Nate Silver's website, they all add up to 1. Probability should add up to 1. These are not probabilities. They're negative, which let's interpret. We'll have to see what that means, and they don't add up to 1. So when you look at such a system, which is in this unfamiliar linear combination or superposition of 0 and 1, what happens? This is what's going on under the hood. But if you observe it or measure it or interact with it to see, well, is it in the ground state or excited state? You do what you would normally do to tell if an electron's in the excited state or ground state. What happens is those amplitudes, those quantum probability amplitudes, so they're like probabilities, but they're a little more general. You square them. So these become 0.5, a half, or 50%. And you'll see one or the other. You don't see something that feels like that. You see one or the other. With probability 50%. He was holding lets vertically polarized light go straight through 100% of the time, but horizontally polarized light go through 0% of the time. Now, if I go this way, you still see me just the same, right? That's this. state here. But put that filter up just the vertical way. Right, you see me, but a little more faintly, right? Just a little faintly. light because you can't really see it. You could slow this down to one particle of light at a time. Click, 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 click. And this particle goes through what's called the beam splitter. Half of the time it goes through, half of the time it's reflected.